Hello and welcome to this class. The topic for the class is correlation. My name is Eunice Frimpon and I'll take you through the class. What is correlation? Correlation is a statistical method used to assess how strongly two numerical, that is, quantitative variables are related. It measures both the strength, how closely, and the direction of this relationship. So correlation helps answer questions like, do longer study hours lead to better grades? Or does memory result in faster software performance? Correlation is useful to detect patterns and make predictions. So there is the variable called the correlation coefficient, which we'll use R or rho to denote. R is used for samples and rho is used for populations. Now, the value of the correlation coefficient usually ranges from -1 to +1. When R is equal to +1, we say that there exists a perfect positive linear relationship between the two variables. And when R is equal to -1, we conclude that there exists a perfect negative linear relationship between the two variables. When R is equal to 0, then there is no linear relationship. So in this example, do longer study hours lead to better grades? The variables to be being considered here are study hours versus students' grades. And then does more memory result in faster software performance? The two variables in this statement are amount of memory versus software performance. So what are the types of correlation? We have the positive correlation, the negative correlation, and no correlation. With positive correlation, as one variable increases, the other tends to increase as well. So, for example, study time versus exam score. Generally, the more time you spend studying, the more likely you are to have a high exam score. So, we'll say that study time moves in the same direction as exam score. As the more you study, the more your grades may be. And then we have negative correlation. As one variable increases, the other tends to decrease. So, for example, number of absences and final grade. So, the more times you are absent from class, the less your grade will likely shoot below. All right. So, as your number of absences is more, your grade will also be decreasing. All right. And then we have the no correlation, where there is no consistent relationship between the variables. So, for example, your shoe size versus your exam performance. The fact that you are size 40 doesn't mean that you will score you have a higher exam score than someone who is size 37. So, your shoe size has no correlation with exam performance. So, the size of your shoe in no way influences your exam performance. So these patterns become clear usually when you plot on a scatter diagram. So if you have some data of the two variables, you can plot them on a scatter diagram like we saw in the previous class and observe the pattern of the relationship. There's a formula we can use to calculate the correlation coefficient. So we have the formula giving us R equals the summation of xi minus x bar, which is the mean, times yi minus y bar, all over the root of summation of xi minus x bar squared times summation of yi minus y bar squared. Now this is yi represents so if x is representing a particular variable, then xi represents the I position. So if we have five students here, so if we have five students, so we have students, hours studied, and then grade. I have students A, students B, students C. Let me keep it at three students. This student, this student studied for 10 hours to write the exam. This student studied for 5 hours to write the exam. This student studied for 15 hours to write the exam. Now, students scored 80%, this student scored 60%, and this student scored 85%. What we see here is I'll let my X variable represent the hours studied, and then my Y variable represent the grade that a student got. So In this case, if X is for hours, then I will say student A is the first student, student B is the second student, student C is the third student. So this 10 is X1, and this is X2. This is X2, and this is X3. So you see that the Xi here, Xi represent the ith student. So X1 is for the first student, S2 is for the second student, and X3 is for the third student. So it means that in this case, I is equal to 1, 2, 3, either of them, all right, based on the students you are considering. So that is how come the notation is like this, and this is what it means. Now, this measures linear relationship between variables. The numerator is the covariance, and the denominator is a product of the standard deviations. So how do you interpret R? If R lies between 0.9, remember that generally R will range from 0, no, sorry. So generally, R will be greater than or equal to -1 or less than or equal to 1. So R will always fall between -1 and 1. R will not be more than 1. R will not be less than -1. So if R lies between 0.9 to 1 or -0.9 to -1, then we say that there exists a very strong correlation between the two variables. If R lies between 0.7 to 0.89 or the negative aspects of it, then we say that there exists a strong correlation between the variables. If R lies between 0.5 and 0.69 or the negative aspect, we say that there is a moderate correlation. If R lies between 0.3 to 0.49 or it's negative, then we say that there is a weak correlation. If R lies between 0 to 0.29 or it's negative, we say there is a very weak or no correlation. Now there's no correlation because when R is equal to 0, there is no correlation. But if I is more than 0 but less than 0.29, then it's a very weak correlation. So the categories are very strong correlation, moderate correlation, weak correlation, and very weak or no correlation. Now notice that we have the positive and the negative side to it. So in this case, this is a very strong positive correlation, and this is a very strong negative correlation. When it comes to the second line, we have the first part to be a strong positive correlation, and this is a strong negative correlation. If you come to the third one, we have a moderate positive correlation and a moderate negative correlation. So you do so for all the other values of R. These are some examples. You can compare file size versus processing time. So the size of a file versus the time it takes to process. To see, is there a relationship? And if there is, how is the relationship like? Is it a positive one? Is it a negative one? Is it strong? Is it moderate? Is it very strong? Is it weak? All right. We also can compare failed login attempts versus the number of incidents. They can compare page load time versus user engagement. You can also compare sleep hours versus energy level. The more you sleep, will it translate into more energy levels? We don't know. So if you have some data, you can plot on a scatter diagram or calculate the correlation coefficient and then use the value of R you get to interpret the relationship. So here's something important to consider. Correlation does not imply causation. Now, what does this mean? Because two variables move together, it doesn't mean that one causes the other. So people who carry lights are more likely to get lung cancer, not because of the lighter, but due to smoking. Okay, so if you are holding a lighter, doesn't mean that you are likely to get a cancer. There's no relationship. The fact that you're holding a lighter does not lead to a lung cancer. No, but if you smoke, that one can lead to a lung cancer. So you realize that the fact that there's a correlation, it doesn't mean that this is causing the other. We also have the Pearson's R. The Pearson's R only measures a linear relationship. The kind of correlation we are looking at, that which formula I introduced a few minutes ago is a measure for linear relationships. So it only detects relationships that form a straight line trend. If you plot the data on a scatter plot, you should see a straight line pattern. If you are seeing a curved pattern, then you can't use the Pearson's R to measure correlation. So when you plot your data, you should see a straight line pattern, either like this or like that. You can't, if you see a curved kind of relationship or a curve like this, then you cannot use the Pearson's to measure correlation. So it works only for straight line relationships. Important notes also, always use a scatter plot before interpreting your R, because a scatter plot will allow you to visually check if the relationship is linear and also spot any clusters or outliers that could distort the value of R. It also helps you identify whether a non-linear pattern exists instead of a linear pattern. Now, correlation coefficient R should never be trusted alone. You should always check the plot first. So here's an alternate formula for R. This is a computational friendly formula. This is the same as the previous one. So if you use this formula to solve for R and you use the previous one to solve for R, you get the same answer. However, this formula is easier to use for computation as compared to the other one. So here's an example. So we have example, calculate correlation coefficients R. This is the raw data where we have some variable x. It's not defined though, but we know that there's a variable x representing something. And then we have the variable y. The data points for x are 9, 2, 12, 7, 16, and 5. And the data points for y are 12, 18, 11, 69, and 16. Let's find the correlation coefficient R. According to the formula, we have n times summation of xy minus summation of x times summation of y all over root of n times summation of x squared minus summation of x all squared times n summation of y squared minus the summation of y all squared. So from the formula, I know that I need summation of xy, I need summation of xy, I need summation of x, I need summation of y, I need summation of x squared, I need summation of y squared. Now with this one, because I'll find summation of x, I'll just fix the value here and then square it. Summation of x is here. Same for this. I'll find summation of y here, so I'll fix the value in here and then square the value. So the four main variables I have to work on is summation of xy, summation of x, summation of y, summation of x squared, summation of y squared. So when I come to the table, I'll have to write out my columns. I need an x column, a y column, an x square column, a y square column, and an x times y column, which I pick from the formula. Now the x variables or the x values are given here. I've listed them. The y values are given here. I need x square values, which are not given. So you just pick the x values and you square. 9 squared is 81. 2 squared is 4. 12 squared is 144. 7 squared is 49. 16 squared is 256. And then 5 squared is 25. So for y squared, you take the values in the y column and you square each of them to fill the y square column as we did for the x square column. So we do all that and we have these values. Now for x, y, this is x times y. So you take your x, take your y, you multiply for each row. So I have 9 times 12 being 108, 2 times 18 being 36. I do so for all the other rows. Now, we move on to find the totals. If you sum all of the x's, you are getting 61. When you sum the whole column of y, you are getting 82. When you sum the whole column of x squared, you have 699. Summation of y squared is 1182. Summation of xy is 612. Now that I have these values, I come back to my formula and I attempt to fix in the values. And here is the number of data points. So if you look, we have 1, 2, 3, 4, 5, 6. So there are 6 data points. So my n is equal to 6. I fix in my 6. Summation of x, y, I pick it from here, which is 6, 1, 2. So I come to fix it here. Minus summation of x times summation of y. Summation of x is 61. Summation of y is 82. So 61 times 82, which I have here. So you look at all the other components of the formula and then fixing the values, pick it from here and fix the values in there. Once we're able to fix in the values, the rest is for us to use our calculator to simplify the expression, all right? So you first of all do the numerator, then do the denominator, and then further simplify until we have our final answer of minus 0.60. So what does this look like? Minus 0.60, first of all, is a negative relationship, and it's a linear relationship. So we have, and 0.6 looks, it's close to 0.5. So we'll say it's a moderate, really. It's not strong and it's not weak. If it's strong, it should be close to 1 or negative 1. If it is weak, it should be close to 0. So because it is not close to 0 and it's not close to 1 or negative 1, it is in the middle somewhere. We say it's a moderate relationship and it's a negative relationship. So we have moderate, negative, linear relationship. So if you want to conclude or interpret this relationship, we'll say that therefore there is a moderate, negative, linear relationship between x and y. So here's a class example I'm going to work through together with you. So please give me your full attention and let's go through this. The data below shows the number of hours 5 students spent preparing for a coding test and their corresponding scores. So we have 5 students A, B, C, D, and E, 2 hours, 4 hours, 6 hours, 5 hours, and 3 hours for each student. And then these are the respective scores. Now the task is compute the Pearson correlation coefficient R. So we move straight to the solution. We have the formula here, okay? But according to the formula, we need summation of x. We already have the x values here, so we leave it at that. We need summation of y. We already have the y values. We need summation of xy. So I'm going to create a column for xy. And then we also need summation of x squared. So I'm going to create my x squared column and then create my y squared column. Let's start filling in the values for these. So xy, we have 2 times 56, 112, 4 times 68, 272, 6 times 75, 450, 5 times 72, 360, and then 3 times 60, 180. Now for x squared, we have 2 squared giving us 4, 4 squared is 16, 6 squared 36, 5 squared 25, and then 3 squared is 9. For y squared, we have 56 squared 3136, 3136, 68 squared 4624, 75 squared 5625, 72 squared 5184, and then 60 squared 3600. Right, so we've filled the columns for x, y, x squared, and y squared. The next to find the totals. So we're going to go straight to finding the totals. Summation of x, we have 2 plus 4 plus 6 plus 5 plus 3, 20. Summation of y, I have 56 plus 68 plus 75 plus 72 plus 60, giving me 331. Summation of xy, 112 plus 272 plus 450 plus 360 plus 180, giving 1374. Then x squared is 4 plus, summation of x squared, 4 plus 16 plus 36 plus 25 plus 9, giving 90. And then finally, summation of y squared is 3136 plus 4624 plus 5625 plus 5184 plus 3600, giving 22169. Right. So the summations have been found. Now it's time to move straight into finding the value of R from the formula. So we have R equals, according to the formula, R equals N. N is equal to 5 because there are 5 data points. 1, 2, 3, 4, 5. So we have R equals 5 times summation of X, Y, which is 1, 3, 7, 4, minus summation of X, which is 20, times summation of Y, which is 3, 3, 1, all over the square root of N. N is 5 times summation of X squared, which is 90, minus summation of X all squared. So summation of X is 20 here. Then I will square it and then bring my big bracket, open another big bracket. We have N, which is 5, times summation of Y squared, which is 22169, minus summation of Y all squared, which is 331 squared. Close the bracket. So given this, the next step is to key in the values in the calculator to find the final answer. So for the numerator, we have 5 times 1374, close bracket, minus, open bracket, 20 times 331, close bracket, equals to 250. The numerator is given 250. All over, denominator is going to be the square root of something. So let's do the first bracket, which is 5 times 90 minus 20 squared, which is giving me 50. The first bracket is giving me 50 times. I'm going to do what's in the second bracket. So I have 5 times 22169 minus 331 squared, giving us 1284. So 50 times 1284. They are all under the square root. So I move on to write 250 all over square root of, what is 60 times 1284? That is 64,200. We have 64,200. So I come back here, R is equal to 250 divided by, what is the square root of 64,200? That is giving me 253.3772. I have 253.3772. So if I divide 250 divided by the square root of 64,200, I'm getting my answer to be 0.987. 0.987. So if you look at this, first of all, it is positive. First of all, it is positive. I'm saying R is equal to 0.99 in 2 decimal places. So first of all, it is positive. So it's a positive relationship. Then moving on, it's very close to 1. So we say it's a very strong correlation. So the interpretation here is that there exists a very strong positive linear correlation between X and Y, right? So this is the conclusion of our solution. So these are the steps you have to go through if you have a question like this, asking for the correlation coefficient and the interpretation of the value of R. Now, these are practice questions for you to try. The first one is the data below shows the age of smartphones and their battery life. So you have 5 different smartphones, how long they have been used, and their battery life. We also have second question, a school records students' shoe sizes and their marked test scores. So you have 5 students, their shoe sizes, and their marked test scores. For each data set, calculate the correlation coefficient R and interpret the result. So referencing the 2 examples we have already looked at, practice these 2 questions also. In conclusion, correlation shows direction and strength of a linear relationship. When R is more than 0, it's a positive relationship. But when R is less than 0, it's a negative relationship. When R, whether positive or negative, is close to 1, we say that the relationship is very strong. So it's close to that when the absolute value of R, when the absolute value of R is near 1, we say we have a strong relationship. But when it's near 0, it's a weak relationship. Always visualize before computing. Visualize with your scatter plot. Thank you for being in this class. I'll see you in the next class. All the best.